All right, welcome to Chapter 6, where we talk about random variables and probability distributions. We're going to look at two different types of random variables today, and we're going to base this on what we just covered in Chapter 5. So in Chapter 5, we talked about how the outcomes of any probability event must all sum to a sample space of 1. This was a very important factor for what we're going to look at here in Chapter 6. A probability model describes, again, the possible outcomes of any sort of chance process and the likelihood attached to each of those outcomes. So we look at flipping 3 coins to get started. So the outcomes we could have are tails, 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 heads, 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 and all of the combinations in between. And we let this random variable, which is typically a capital letter, be some sort of specific outcome with those coins. And in this case, we're looking at the random variable of the number of heads. So the number of heads. We could have 0 heads, 1 head, 2 head, or 3 heads. And you see how flipping the 3 coins creates it so it's not equally likely. Okay? There's a 1/8 probability of 0 heads, just like there's a 1/8 probability of 3 heads, and then 3/8 for everything in between. So this chapter is a little bit different from last chapter because we looked at the outcomes of a die last chapter, and we easily could put the 2 through 12 on here, and you could see that each one has their own unique probability. That's exactly what we're looking at here. So from a table, we could turn the probabilities into a histogram. And we look at now what is very specific is a random variable. What is new on this slide compared to Chapter 5 is a specific variable of interest. We're not just flipping 3 coins. We're looking at the exact amount of heads. That's the important new part here. A random variable takes numerical values. So our numerical values here would have been 0 head, 1 head, 2 head, or 3 head. And in the probability distribution of a random variable gives the possible values followed by the probabilities that they take. So all of the possible outcomes and all of the probabilities linked to them. And notice how it's very important that the probabilities still do sum to a total of 1. There can't be missing probability or missing outcomes. So in general rules here, it is called a discrete random variable. What makes this a discrete random variable is that the outcomes are fixed. I can get outcome of 0 heads, or 1 head, or 2, or 3. There was no 1.5, 1.55, 1.555, 1.55555. It was fixed certain outcomes, which makes it a discrete random variable. So when x takes a fixed set of possible outcomes, the probability distribution of a discrete random variable x lists the values with their particular probabilities. Each one of these probabilities, just like Chapter 5, can only be a number between 0 and 1, and the sum of all of the probabilities has to be 1. No missing probability. To find the probability of any event, just add the probabilities of the outcomes in that event. So if I said 0 heads or 1 head, I would look at the 0 head and the 1 head and add them together. That's what that third thing says to do. So when you think about a probability distribution for a random variable, there is a mean to it, meaning we call it the expected value. What do you expect to happen? When analyzing a discrete random variable, we follow the same strategy we use for any quantitative data. We look at the shape, we look at the center, we look at the spread, we look for outliers. The mean of a discrete random variable is the average of its outcomes, but each one just has a weight to it. It's like a weighted average. Okay, there's more chances of getting a 1, so it has a higher weight. So how do you find the mean? You take an outcome, times it by its weight, meaning probability. Add it to an outcome, times it by its weight. Added by an outcome, times it by its weight. Add them all up. That's it. The reason for the mean formula, which used to be add them all up, divide by how many you have, is they were all weighted equal. So this P1, P2, P3 handles the whole that we used to divide by how many you have. This is dividing it into unique pieces, a weighted average. Let's see what it looks like for this example that we're going to use. A baby's APGAR score. So when a baby is born, the nurses and doctor agree on an exact score on the health of the baby, the delivery health. So X will be our APGAR score of a randomly selected newborn. The values of an APGAR score are 0 through 10. Okay? Compute the mean of the random variable, and we're going to interpret what it means. So you can see here that it's not like every baby gets a score of 0 through 10 in an equal distribution. So I can't just all add it up and divide by the 11 items here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, 11 items. You can see here that 6, 7, 8 and 9, sorry. 8 and 9 get the majority of the probability here, over 70%. So they should be weighted higher. So how does it work? Okay. We see that 1 in every 1,000 babies has an APGAR score of 0, 6 in every has an APGAR score of 1, and so on. So our expected value is the sum outcome times probability plus outcome times probability. Add them all up, 8.128. So lot of typing, lot of work there. We'll see if there's a shortcut shortly. But you have to know what it means. You have to know what this means. The mean APGAR score of a randomly selected newborn is 8.128. This is the average APGAR score of many, many random chosen babies. So the mean of a random variable, you have to remember that it is the average score over many, many repetitions. It is the average score over many, many repetitions. It does not mean that one baby will have an APGAR score of 8.128. No. It is the score, the average score over many, many repetitions. So if you have a mean, you have a standard deviation, because if you have a center, you have a spread. Since we use the mean as the measure of center for a discrete random variable, we will use the standard deviation as our spread. The definition of the variation of a random variable is similar to the definition of the variance of a set of quantitative data. So how does it work? It works by taking the outcome minus the expected score, which we call the mean of the random variable. Little new data, little symbol here. Let's do a symbol check. Mean was always mu, and now we're doing sub x because it's for the random variable we named x. So mu sub x is the expected value or average or mean of a random variable. The variance, capital VAR, var of capital X, is outcome minus its mean times its probability, plus outcome minus mean squared times probability. Outcome minus mean squared. So you add all of those up. That will be the variance. To get the standard deviation, just like we did in chapter 1, section 3, square root the variance. So we have variance and standard deviation. It's going to be much more important to remember the difference between variance and standard deviation. Standard deviation is the square root of the variance. Well, it would take a whole lot to compute this. You would have to do the APGAR score minus its mean, square it, times its probability, add it to the next one. And yes, if you choose to not use your calculator, you would have to calculate this whole thing if you don't choose to use the shortcuts of the calculator. So let's talk about what this means. Let's talk about an interpretation, because it's better to know what the scores are you're finding. So our variance came to 2.066. Look at what variance is. Variance was our sigma symbol for subscript x, that's this random variable x, and squared, because sigma x was standard deviation. So square it, you have variance. So sigma x is 1.437. What does that mean? You need to know an interpretation. So what does it mean? It means a randomly selected baby's APGAR score will typically differ from the mean by 1.4 units. Again, this is in many, many repetitions. So in many, many repetitions, a randomly selected baby's APGAR score typically varies from the mean by 1.4 units. Okay. We just talked about a discrete random variable. So to finish it, how would I find the mean and standard deviation on my calculator? Okay. Very simple. Stat, edit. The outcomes the variable takes, just like they did in chapter 1, go into list 1. What is new here is we have list 2. I put the APGAR score probabilities. So I have my APGAR scores in list 1, the probabilities in list 2. This is still one variable. So I go to stat, I go to calc, I go to one variable stats. It's a variable called APGAR scores. My data is in list 1, and right there, what is blinking right now on the screen, we now have a frequency list because it has weights, it has probabilities. So typically we left frequency list completely blank in chapter 1. Now you put list 2 in because your probabilities are in list 2, and it will do all of the work for you. Here's the mean of 8.128. You will see here the calculator's a little picky, but it's okay. You'll never make the mistake because it leaves SX always empty. You do have to use sigma x here of the 1.43. The typical variation from the mean in many repetitions is 1.43, and the average score over many repetitions is 8.12 for the APGAR scores. Just like that in the calculator. Again, stat, calc, it is one variable stat still, but the new thing is you have a frequency list. So now we're going to get into a continuous random variable, meaning it can take every single score. There is everything in between. Any data point can have one between it. So arises from situations that involve continuing something, counting something continuously. Situations that involve measuring something are often continuous. So counting is discrete, continuous is measurements for the most part. A continuous random variable, still capital X, takes on all values in the interval of numbers. The probability distribution of X is described by a density curve. Remember density curves? The probability of any event is the area under the density curve. We've done this before. The probability model of a discrete random variable, X, assigns probability between 0 and 1 to each possible value. You know this answer. Since a continuous random variable is infinitely possible, all continuous probability models are 0 to an individual outcome. It was the same thing in chapter 2. It's the same thing if you ever in calculus tried to integrate with the same lower and upper bound. The area under a continuous curve at a specific point is 0. So we use intervals to get probability. We have an opening part of the interval and a closed, just like we did with normal CDF and inverse norm. This is going to be sort of a repeat of normal stuff. So here we are. This will feel very familiar. The height of young women closely follows a normal distribution with mean of 64 and standard deviation of 2.7. Now choose one young woman at random, call her Y, her height Y. So there's our random variable. We're going to find the probability of one person's height Y. If we repeat the random choice many, many times, see this whole chapter just says many, many times in repetition, the distribution of values of Y is the same normal distribution that describes the height of all young women. Many repetitions creates a repeated curve for all. So what is the probability a chosen woman to be 68 to 70? Think for yourself right now. I have a 68, I have a 70, I have a mean, I have a standard. What will you use to calculate this probability? Area under the curve, normal CDF. So we would, if you wanted to use a Z table, you would find the lower Z score, the upper Z score. You would go to the Z table, find the two values, or we can use normal CDF. I'll show you on the calculator. We have 68 to 70, 68 to 70. Let me just remind you on the calculator. So we have second distributions. This is a norm CDF to find area under a curve. We're going from 68, we're going to 70. The mean was 64, and the standard deviation was 2.7. This is how we can find area under the curve for a random variable of one person's height, one female's height over many, many repetitions, 0.056. And we go back and we see they got 0.056. The probability is the area under the density curve. So we've done way lots of density curves and area. I wanted to just close with an example today of just looking at the discrete random variable one more time. Let's take a look at this. This is question 14 from section 1. What it says is a life insurance company sells term insurance to 21-year-old males and pays $100,000 if the insured dies in the next 5 years. Pretty crazy insurance plan. So they sell it to you at 21 years old, and if you make it to 26, the insurance policy is over. This is basically insuring if someone's going to die or not in between the ages of 21 and 25. I guess those are the riskiest years, so I guess that's why this question is about. So how's it work? Every year to have this insurance policy, you pay $250. You pay $250 a year to have it. The amount Y, this is our random variable. Capital Y is the company earns on the policy at $250 a year. So our random variable is created by saying how much does the company earn off each person. Okay, here's the partially completed table. So how's it work? Let's go over the table. We're looking at age of death, and we're looking at the profit of the company because that was our random variable. So if the person was to die at 21, let's see why they would lose $99,750. This is also the same question as letter A because it says, why does it die if they died at 25? Do they lose 98? Okay, for all of these, let's think how they're come about. At year 21, the company would have only collected $250, and unfortunately, the person of the insured passed. So the company paid $100,000, but only brought in $250. So their net loss is this much. Year 2, they collect $500, but lose $100,000. Year 3, collect $750, but lose $100,000. Year 4, collect $1,000, but lose $100,000. And year 5, collect $1,250 and lose $98,750. But at 26, meaning if the person just lives for 5 years, the company would have profited $1,250. So letter A, why do they suffer a loss? Because if the person dies, they have to pay out $100 and only collected this much. Find the missing probability. How does probability work? This plus this plus this plus this plus this plus the missing number must sum to 100%. So how does it work? Take 100% or 1, subtract what we know. The probability the company makes the $1,250 profit, meaning the probability of this last outcome, is all the way up at 99.05%. So this seems risky, but let's see why not. What does the insurance company's mean? The insurance company's mean, which you would put it in a calculator, outcome times probability, outcome probability, add them all up, is $303. What does it mean? Interpret it. If the company insures many people, they will make about $303.35 per life insurance policy. Okay? Again, in many repetitions, they expect this amount. Follow-up questions. It is quite risky for you to insure the life of a 21-year-old under this example. There is a high probability that your friend would simply live to 26 and have to pay the $1,250. But if he were to die, you would lose almost $100,000 as an insurance company. Explain carefully why selling insurance is not risky. Selling insurance under these terms is not risky because they insure many, many people. Sure, they would lose a lot of money for this, or this outcome. But the probabilities are so small, and they're going to insure many, many people, they would actually expect to make $303 per person in the long run. Letter A. Even though the company would lose a large amount of money in a small number of subscribers, policyholders. That's not how they work. They insure many. And because they insure many men, they would tend to make an average of $303. And in the last question, letter B says, there's a lot of risk. The risk is found by the standard deviation, meaning the typical variation. What is the typical variation here? The typical variation is the variance of 94. This is our variance, that giant number, 94 million. So our square root of that is $9,707. The typical variation from the mean is $9,000. So they can vary a lot higher, or they can vary into the negatives, 303 minus 9,000, but it's the typical variation. So the more variable the return is, the riskier the investment. I'm not sure how volatile that is, but it is the variation. So that's it for 6.1. You're going to work on discrete and continuous random variables, and keep in mind that these things happen over the long run outcomes.